we'll study inverse Z transform. The theory we have discussed when we were discussing about Z transform and inverse Z transform purely from mathematical point of view. So if you have any confusion, you can go and look at there. But the basic definition is, if this is xn, the Z transform is xz. And what is xz? Xz is n equal to minus infinity to infinity, the sequence, and then z minus n. This is the transformation, and this is inverse transformation. That is, inverse transform of z inverse of xz is xn. Simple. So how we do that? That we have to understand. So let's start with our first example. This we will do by using partial fraction method. See, how can we expand this function? We can write it as a by 1 minus 1 by 4 z inverse plus b by 1 minus 1 by 3 z inverse. See, before I proceed, region of convergence is very important, because for different regions of convergence, the sequence will be different. How? Let me solve this first, and then I'll just explain to you how it differs. See, so this will be a minus a by 3 z inverse plus b minus b by 4 z inverse by this 1 minus 1 by 4 z inverse into 1 minus 1 by 3 z inverse. Okay. So comparing it with this, a plus b is, see, a plus b is 3, and a by 3 plus b by 4, a by 3 plus b by 4. Okay, this is b by 4, a by 3, this is 5 by 6. This is also minus, this is also in minus. So let's solve this. What we'll do, let's divide throughout by 3. So this will be a by 3, this will be b by 3, this will be 3 by 3, that is 1. Okay, and then this minus this, a by 3 minus this. So this minus this will be b by 3 minus b by 4. And this side will be 1 minus 5 by 6. This will be 1 by 6. And this is 1 by 3. So this is 12. 4 minus 3. So you have, this is 1 by 12. So b is 12 by 6. That is 2. So b is 2. And here it was a plus b equal to 3. So when b is 2, a is equal to 1. So we have a equal to 1, b equal to 2. So we can write this equation, a equal to 1, b equal to 2. So this is our equation. Okay. What is the inverse of this? If you remember, an, un, this was our first example in the last video when I started Z transform for signals. This was the first example. The Z transform of this is 1 by 1 minus a z inverse for z greater than a. This was the condition. Okay. If the region of convergence is this, z is greater than a, then 1 by 1 minus a z inverse will give this sequence. Try to understand this. We will solve this example only in 3 different regions of convergence. The first is this one, z greater than 3. So when we were discussing this problem, we learned that this xz is equal to this xn when z is greater than a. That is, in the question it's given this is greater than this. Our a is 1 by 3. Since it is greater than 1 by 3, therefore, and 1 by 3 is greater than 1 by 4. So this will be equal to 1 by 4 to the power n un for z greater than 1 by 4. Since the region of convergence, if you see this properly, let this be 1 by 4, this is 1 by 3. Since we are talking of this, obviously this 1 by 4 z greater than 1 by 4, it holds true for z greater than 1 by 3. Okay, so this is the value, and plus twice 1 by 3, that is a to the power n un, because z is greater than 1 by 3. So for this expression, this xz, since the region of convergence is greater than 1 by 3, therefore both these expressions give this sequence. So our xn is this, for, again I am writing, for z greater than 1 by 3. Okay. So this is our first example. Now let's see example 2. It's same here, but what we will change is, let Z be between 1 by 4 and 1 by 3. Then what? See, let me explain this. This you must have written by now. So this was our first answer. Now understand it properly. This is 1 by 4, this is 1 by 3. Okay, this is the real line and this is the imaginary line. This is Z plane. First example we saw, Z was greater than this, that is this region. For this region, this was also, this holds true for this also, because this is greater than, we are talking of this point or this point, which is greater than this. Therefore, a to the power n un, the Z transform is 1 by 1 minus a Z inverse. But the second example that I had discussed was, I'm writing here for Z greater than a. Now, second example that I had discussed was for Z less than a. If Z is less than a, then this 1 minus a Z inverse, this xz, actually it is the Z transform of minus a to the power n u minus n minus 1. This we have seen. If you don't remember, you can go to my last video and see the second example. But try to remember that when the region of convergence is greater than this, this gives this sequence. But when it is less than this, that is, if it is inside this, then let me talk of 1 by 3. When we talk of 1 by 3, if Z is greater than 1 by 3, the answer will be 1 by 1 minus 1 by 3 Z inverse. But when it is less than, when the region of convergence is less than 1 by 3, then this will be, this xz will be, the sequence will be minus 1 by 3 to the power n u minus n minus 1. So this has to be kept in mind. Okay. So now our question is, that is, it lies between this, that is, the region of convergence is this. See. So what happens? The region of convergence is this. This means for Z greater, this is Z is greater than 1 by 4. So this will apply. This will give this sequence. But Z less than 1 by 3, this will give this sequence. This will give, it was 1 by this plus 2 by this. I'm writing it again. Our xz is 1 by 1 minus 1 by 4 Z inverse plus 2 by 1 minus 1 by 3 Z inverse. So xn will be, since it is greater than 1 by 4, so no issue, this is 1 by 4 to the power n un. But it is less than this, so this will apply. So we'll get minus, there we have a minus, I'm rubbing this. So minus 1 by 3 to the power n u minus n minus 1. Okay, so this is the expression. For same xz, when Z lies between these two, we have this expression. Third, let's go further take. This is the expression for this. If Z is less than 1 by 4, then if the region of convergence is this, then what? Then both will be this expression only. Both will give this expression only, because the region of convergence is within that circle only. So what we'll get? In place of this 1 by 4n, our this expression will also be minus 1 by 4 to the power n u minus n minus 1. This is xn. Clear? So again, I am giving you a brief that you have to, I am rubbing these all, okay, and I'll give you a little bit of explanation. What you have to keep in mind, that our xz is 1 by a Z inverse. This is inverse, this is Z transform of a to the power n un for Z greater than a. The region of convergence is greater than a. So this gives this, or this gives this when Z is greater than a. Secondly, same expression is for minus a to the power n u minus n minus 1 for this less than this. So you have to keep in mind, when you see the question, you have to see what is the region of convergence. Because if you get a question for this, the region of convergence is given this, and you do give the value for this Z greater than a, you will be mistaken. Okay, you will do mistake. So learn this properly, keep this in mind, solve 2-3 times, transform and inverse transform. Everything will get into your mind. Okay. Now our xz is this. We have already solved this type of question. I'm again giving you a recap what it is. See, xz is, our definition is n equal to minus infinity to infinity x n z minus n. Okay. Now if our xn is impulse function, that is del n, what will this value be? It will be, this del n will be 0 for all values except for n equal to 0, and at n equal to 0 this will be z to the power minus 0, that is z to the power 0, so this will be 1. So wherever you have any constant as a number, let's say the number is k, and you have to take inverse z transform. So what will be the this is z plane. So if you take inverse z transform, what it will give? It will give k del n. Simple. Okay. Now second, if instead of this we had taken del n minus 1, at n equal to 1 this will be 1, and at n equal to 1 this will be z minus 1, that is you will get z minus 1. So this is what? This is 4 del n minus 1. If you put n equal to n plus 1, so at n equal to minus 1 this will be 1, n equal to minus 1, sorry, at n equal to minus 1 this will be 1. So and at n equal to minus 1 what it will be? This will be z to the power 1. So this is z. So 2z will be 2 del n plus 1. That is to say, if we generalize this, let's generalize it. It's a del n plus n0 z minus n. So this will be del n plus n0. This will be 1 for n equal to minus n0, and otherwise it will be 0. This you understand? So at this n equal to minus n0, you put minus n0, so what you will get is zn0. Okay, so you should keep this in mind, that is del n plus n0, a simple transform pair you should keep in mind, z transform pair, this gives zn0. Okay, now keeping this in mind, if you solve this question, it is very easy. See, so xn will be 3 del n plus 2, then 2 del n plus 1, then this is 1, so it is simply del n, and finally this is 4 del n minus 1. So this is the sequence. The same problem, that is a to the power n un. Let's solve it by power series method. You will get question to solve by power series method. So you may get in values, I'll use a, that is what I am saying is 1 by a z inverse. You may get 1 by 1 minus 1 by 3 z inverse or 1 by 4 z inverse. I am using just alphabet, just an alphabet, so you can use it. So the z inverse transform is, I have told you, this is an un for z greater than a. Okay, when the region of convergence is this, and it is minus a to the power n u minus n minus 1 for z less than a. This we know. Let's solve it by power series method. How? See, fifth example, 1 by 1 minus a z inverse. So how do we expand in power series method? By division. So this is 1 minus a z inverse 1. This is the case. So what we do? We multiply it by 1. What we get? We get 1 minus a z inverse. So subtracting, what you will get? A z inverse. Then what you have to do? You have to multiply by. So this will be multiply by a z inverse. What you will get? A z inverse minus a square z minus 2. So what you get is a square z minus 2. Then multiply this by a square z minus 2. What you will get? You will get a square z minus 2 minus a cube z minus 3. So what you get is a cube z minus 3. So you see there is a pattern. This is a series, a power series. So this can be expanded as a 1 plus az minus 1, a z minus a square z minus 2, a cube z minus 3, and so on. Now, if az inverse is less than 1, you know progression. So if this is less than 1, if this be r, then it is 1 by 1 minus r. This you know, only when r is less than 1. So if this is less than 1, this means, see, a by z is less than 1. So it means z is greater than a. So in this situation, you can write this 1 by az inverse, this sequence becomes this thing, and in n terms, this is basically minus infinity to infinity, not minus infinity, from 0 to infinity, and what you get is, see, it is a to the power, or az1 to the power n. This is the expansion from 0 to infinity. There, because of this, we use un to denote 0 to infinity. Minus terms vanish. So this is the expansion. So we have expanded this using power series method. So the inverse Z transform for this is a to the power n un. Okay, first one. Now we'll go to the second way. That is when mod of Z is less than mod of A. Then what? See, if it is, this ratio is, if when it is less than 1, we were able to do this. But what if the ratio is greater than 1? If the ratio, this is greater than 1, this means what? It means Z is less than A. So in that case, that series won't converge. You understand? 1 plus r square plus r square. Since r is greater than 1, it won't converge to 1 by 1 minus r. So what is the way? See, we'll divide it like this. 1, instead of 1 minus this, we'll write minus az inverse plus 1. Just reverse it. 1. So what we'll do? We'll multiply it with a inverse z. What you will get? And minus. So what you will get? A inverse. So this will be 1 and this will be 1. So this is 1 and this is minus. What you will get is a inverse z. So what you get is a inverse z. Okay. Now second multiplication, multiply by a minus 2 z square. So when you multiply this by a minus 2 and this is a, so what we will get is a inverse and then z inverse z square. So z, okay, this you will get, and here you will get minus 1, that is a minus 2 z square. So what you get is a square, sorry, a minus 2 z square. That is, you will get series like this. The series will be like this: minus a inverse z, minus a minus 2 z2, minus a minus 3 z3, and so on. So this is the series that you will get by power series method. Okay. So what you can write for this? You can write the expansion will be like this. This is for n equal to 0 to infinity. So what we do? We put this as a inverse z to the power n. But for 0, this will be 1. We don't have this term. So this actually goes from n equal to 1 to infinity. That is 1 by 1 minus a z inverse. It is this thing. See, and minus term. Minus also because this is it. So when you put 1, it is a minus 1 z, this term. Then 2, a minus 2 z2, this term. So we have represented this series. If you look at properly, this series is actually equal to, if you put n equal to minus n, then this will be n equal to minus infinity to minus 1, and this will be a, this is minus n now. Okay. So what you will get? You will get a minus n, so this is a n and z minus n. Okay. So again you get a n, but the only thing is, that is what I am saying, again the sequence is this, but there is a difference. What is the difference? First is the region of convergence is this. Because of this, you get this. But see, this is from minus infinity to minus 1. That is on n scale. If this is 0, this is minus 1. So this is the part. So how we'll write this? We will write it. This is minus. So we'll put minus, then a to the power n. And to represent this, what we do? U minus n minus 1. Series is left sided. So now you get the same question. This is 6. Okay. I think this is clear to you. What I advise, you should go revise this 3-4 times. All the 6 questions or the 6 examples that I have discussed, you should revise them 3-4 times. Then it will get into your mind. Let's see our final question on inverse Z transform. And after this, we will start properties of Z transform. But let's see our final 7th question on inverse Z transform. Our xz is log 1 plus az inverse, and given z is greater than a, then what? We have to find x in. How we can find? See, log 1 plus x from power series, if you know expansion using Taylor series, it comes to x minus x square by 2 plus x cube by 3 minus, and so on, up to minus 1 to the power n plus 1 x to the power n by n, and so on. This is the series. This is power series, Taylor series, actually using Taylor series. So we'll expand this like this. So from here we get xz. This will be summation of n equal to 1 to infinity. Let me put this first. It will be minus 1 to the power n plus 1. Then az minus 1. This is x to the power n by n. Now why not from 0? Because if you put n equal to 0, this won't converge. So this has to start from 1. N equal to 1 to infinity. This is the value. So when you are saying this 1 to infinity, your xn will be minus 1 to the power n plus 1, a to the power n by n, and this is n minus 1. Okay. So let's see properties of Z transform. First property is called linearity. We have seen these properties earlier also when we were dealing with Fourier transform, when we have studied Laplace transform and so on. So let's see what is linearity property of Z transform. If for a sequence x1n, the Z transform is x1z. For region of convergence, let's say R1. This is the region of convergence for x1n. That is let. Second sequence is x2n, which is x2z for ROC equal to R by 2. Then, according to the linearity property, for some arbitrary multiplication by some arbitrary constant a x1n plus b x2n, the Z transform, or from here to here, the inverse Z transform will be a x1z plus b x2z. The only issue is, this is very simple. The only issue is, what will be the region of convergence of this combined sequence? The region of convergence will be R1 intersection R2. Okay. When I was giving some examples on Z transform, if you remember that example where I have used this example, b greater than 0, there you had seen that there is a region of convergence between 1 by b and b. This property holds true. So as an example, you can go and look at that particular example. Okay, so this is called linearity property. The second property is called time shifting. What is time shifting property? Very simple. If xn, the Z transformation pair is xz, z with region of convergence, let's say R, then xn minus n0, we have done this in our last video also, xn minus n0 is basically z to the power minus n0 into xz. Simple. That is, we had seen for impulse functions, del n minus n0 is simply z minus that. What will be the region of convergence? Region of convergence will be R only, but with exceptions. And what are those exceptions? Exceptions are the poles that have been introduced by z minus n0. Let's say it is 1 by z. Then at a z equal to 0, you have a pole. So that will be an exception. Or if this is z, simply multiplied by z, that is for n plus 1, then there will be a 0 at z equal to 0. So the region of convergence will be R, but with these exceptions. Scaling in the Z domain. Third property is scaling in the Z domain. what is it? If this is the transform pair with ROC R, then if you have certain arbitrary constant Z0 to the power n x n, you multiply this, then it is basically Z by Z0, and the region of convergence will be, Z0 into mod of Z0 into R. Why I am telling you these properties? It will be very handy for you to solve questions. For example, if you know that for, let's say, we have certain xz for which the output is a to the power n un. We have seen this. Then if x is z by 2, then this will be a by 2 to the power n un. Okay, and the region of convergence will be, for here we know the region of convergence is this. So for here you will have z0 into the original, so that is this into 2a. So this way these properties help you solve problems very fast. Instead of going through all the normal procedure, you can simply write the answer. So this was third property. Now let's see fourth property. It is time reversal. What is time reversal? If xn z transform pair is xz, ROC is R, then x minus n, this sequence has, the transform pair will be x 1 by z, x of 1 by z, and the region of convergence here will be 1 by R. It is very useful property. Fifth property is called time expansion. What it is? Time expansion. What is this property? If you remember this, we have used when we were explaining discrete signals. Xkn is given as x of n by k for, or if n is a multiple of k, otherwise it is 0. This is function. So the z transform of this function xkn, the z transform of this function, or I should write like pair, is basically xz to the power k. This is time expansion. So if you know what is xz, and you have to find this function, that will be z to the power k only. And if the original region of convergence was R, now the region of convergence will be this. That is for xn xz pair. If the region of convergence was R, this is R to the power 1 by k. Okay, we'll see examples. We'll understand what is this. This is very easy. This will make your problem solving very easy. Sixth is conjugation. You know what is conjugate? Complex number. X plus iy, x minus iy are conjugates. So this was property 5. So this is property 6, which is conjugation. For xn, this always keep in mind, we are talking about this transform pair, and the region of convergence is R. So if this is the case, then for conjugate of this sequence, the transform pair will be, it will be conjugate of this, and the region of convergence will be same, R only. We have seen this. When I was giving you an example, I don't remember, it was like this: 1 by 3 to the power n sine pi by 4 n something. We have solved this example. You can go and you can correlate that the region of convergence was same. We had a conjugate, something minus this by this e to the power this, and then plus e to the power minus j pi. We had these two conjugates, and we had found that the region of convergence for both was same. Why? Because mod of this is 1, or e to the power minus j theta is 1. So region of convergence is same. Okay. Now let's come to 7th, that is convolution property. We'll just see some properties, 1-2 more properties, and then we'll solve some problems. The 7th is the convolution property. It says if x1n, The transform pair is this. Region of convergence is, let's say, R1 for this, and X2n is X2z. Region of convergence is R2. Then X1n into X2n. This is convolution. This is the sign of convolution. That is convolution of X1n and X2n. The pair is, transform pair is, it is simple, X1z into X2z. So this is very simple. We'll see example and understand this. This is very helpful in solving problem. The region of convergence will be R1 intersection R2. Okay. So this is the 7th property. The 8th property, we have seen it. We have already seen it. Let's see it as a property. It's differentiation in the Z domain. 8th property, differentiation in the Z domain. If the transform pair is this, the region of convergence is R, then if you have n into xn, we have seen this. If you want to go into detail of this, you can go to my mathematical treatment of Z transform. There we have solved several examples on this. So the transform pair is basically minus z d by dz of xz, and region of convergence is this only, R only. Okay. This is also very helpful to find. If you know xz, you want to see this or this to this, this is very helpful. I'm giving one more property and then we'll see some examples. The last property is initial value theorem. What it is? Initial value theorem. So this video will end on this property, but we'll see some more properties later on. Initial value theorem says if you have a sequence xn, which is xn is 0 for n less than 0, that is it has value for n greater than equal to 0 only, then if you want to know what is x0, what is x0, that is limit n tending to 0 xn. You can write it like this. So according to initial value theorem, it is equal to limit z tending to infinity xz, where xn and xz are Z transform pairs. Clear? You want to find the value of this sequence at 0, it is limit z tending to infinity xz. Okay. So we have seen so many theorems. Let's see some examples. Now let's see a very good example on convolution. We have to find yn, which is convolution of this and this. Now convolution of this and xn, it is very easy to find using convolution theorem. Why? See, this you know, del n, the Z transform pair is 1, and del n minus 1, it is Z minus 1. This we have seen. Del n minus n0, the transform pair is Z to the power minus n0. We have seen this. Therefore, this is what? That is, if you talk of yz, it is what? It is hz into xz. Hz, xz. Hz is what? It is 1 minus z inverse. And this is xz, or it is xz, z inverse xz. So what is yn? Now if you take inverse transform, it is xz is xn, and this is from time shifting property. We have seen z to the power minus n will be n minus n, sorry, z to the power minus n0 will be n minus n0, that is this becomes n minus n0. Sorry, no, n0 is 1, so this is n minus 1. So this is your yn. It is so simple using convolution theorem. Okay. See, this is a very simple example. You know, for an un, the Z transform pair is 1 minus az inverse. If you take na to the power n un, so the Z transform will be, multiplying this by Z will be d by dz of, sorry, minus z d by dz of what? 1 by 1 minus az inverse. Now if you do this differentiation, you will get this. So the new function is this. The sequence in n sequence is this. Okay. So this you can use it whenever you want. Whenever you have a sequence and you have to multiply by this, or whenever you know the exact function which is differentiation of something, so you can correlate and get the result. Okay. Similarly, if let's say our Let's say our question is 1 minus a1 z inverse. Why? 1 minus a z inverse square, and we have to find x is 0. So from initial value theorem, we know this is limit z tending to infinity xz. So if you put z infinity, this will be 0, this will be 0. So the answer will be 1. So this is how we solve problem using initial value theorem. Very easy. So what I suggest is revise these topics many times and try to solve problems from your book.